Recording now. And I'm going to become a human. All right. Anybody have any questions? Anything? Oops, that's the wrong thing. Oops. No, that's the wrong thing, Jeff. No, that's definitely the wrong thing. No, I don't need that right now. Okay, there you go. Sorry. Very sorry, I apologize. That was mostly for me. I get a kick out of that. Any questions from homework stuff, guys? We got the quiz happening today, starting after class. So even if you don't ask any questions, I'm going to ask questions for you because you should have questions. Anything, any questions? Like, what is the quiz on, Jeff? Does somebody know?
5, 5, and 5, 7.
Well, 5, 5, 5, 6, and 5, 7, yeah.
Yeah.
Yeah. Let me see. In fact, 5, 4, I don't think was on the last one either. So, I mean, it's going to have, it's going to have Descartes, it's going to have bounds, it's going to have rational functions that you have to graph, right? So it's going to have asymptotes, it's going to have slant asymptote, it will. It's going to have finding intercepts and stuff. All right. How many questions? Let me see. Let me pull it up here. I didn't count. Dadgummit. I don't know how many questions the damn thing has. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Counting all the A, B, C, D stuff. So it's really not that long of a thing. Let's see. And on the problem where you have to make there's going to be a list. You have to make the list of all possible rational roots. You're going to have to do that. I give you a hint. I give you several hints, actually. So you're going to have kind of a long list, but it should chop down. It should chop down. It should chop down. And then I give you a hint there to get you started. So depending on how much you pay attention to the hints I'm trying to give you, that one might take a little while. So you just got to know your Descartes. You got to know your bounds. Yeah. Okay. Any specific questions? I did have one from office hours. That was just a general question about, can we do a problem from 5, 6, which is a great question to ask. That covers everything. So let's try it. Let's do a problem. Let's see. If nobody else has any specific questions, I'm just going to pick one from 5, 6. Whoa. All right, here we go. Yeah, let's pick one. Okay. Let's see. Yeah, that one looks gross. Let's try that one. Let's see. Neat. Well, let's find out. I have no idea if this is going to factor. Let's find out. Well, let me do this too. It's all about me. Bam. All right. All right. So let me copy this down up on the board. All right, I got some new pens. Thank God. Some new markers. All my markers are dead. All right. So let's try this. Okay. That looks gross. I like it. I don't know. Yeah, that'll work. Okay, good. All right, guys. So I would step you through the process. So the first thing I would ask is, well, let's see, which way, I don't know, I can't remember now. Find the intercepts, find the asymptotes, right? So find all the intercepts. And when I say that, that means X and Y intercepts. Don't forget that, right? Both. That's why I say all intercepts. How do I find the X intercepts? What would I focus on?
On the top, numerator.
Oh, Julius, can you hear me? Where's Julius at? Were you having trouble? I don't know, something's weird with the speaker stuff tonight for everybody. I'm gonna just back out. Oh, Julius, you can't hear me? Okay, do what you gotta do. Sorry. All right. Everybody else can hear me, I guess. You know, if somebody says no, that would be kind of funny, but it's too late now. Okay. So I'm sorry, say it again. Focus on the
Numerator.
numerator. Does everybody understand why? The only way that a fraction can be 0 is if the top is 0. I like it. So everybody take a minute and factor that. Julius, you back? Can you hear me? Okay, good. All right. Coolio is right. Or cool beans, like we used to say. Cool beans. Now, this is a problem where I wouldn't do any things, I wouldn't do 3 times that, because 3 has only one way to do it. And 5 has only one way to do it. But it's all about, do I put 5 here or do I put 5 there, right? So obviously I should put 5 here because that would make 15. So I'd have 15 and 1. Do you guys see that? I mean, when there's not a lot of factors to these, in fact, when there's only one factor to both of these, that's what I should focus on. I don't have to do much else. I like it. And now I got to figure out the signs. I know they have to be different signs, and I know the bigger one has to be negative. So this one has to be negative. Bam. Because here's my 15. Here's my 1. Negative 15. Bam. Okay. So I get negative 1/3 and 5. Okay, I like it. So to be official, negative 1/3, 0, and 5, 0. So I'm going to kind of collect this up here because obviously I'm going to have to erase all this. So negative 1/3, 0, 5, 0. What's my y-intercept now? My y-intercept.
Five over 16.
5 over 16. I like it, right? Just put a 0 in for x. All this stuff dies. 5 over 16. Cool. I like it. Then I would ask you asymptotes. Let's start with the ha, right? Ha. What's the horizontal asymptote? What situation am I in? Yeah, so I'm in the situation where the degrees are the same. So I take the leading coefficients and find their ratio. So the horizontal asymptote. Now be careful. Don't write this. That's not right. The horizontal asymptote is not a number. It's a line, right? Okay. I like it. So on the homework, if I'm like circling right there, put little question marks, now you know what I mean, right? And you can think of it as being picky, and I don't give a shit. You just do that. All right. So how do I get the vertical asymptotes? What do I have to do for that?
Focus on the denominator.
Yeah, shit. I got to factor this thing now. This looks a little bit worse. So go ahead and do that. I'll wait. Because the vertical asymptotes are walls. that I set up for my x's that I can't use. I will talk about removable discontinuity. Does that sound familiar to anybody from the homework? Nobody brought it up. I'm like, is somebody going to bring it up? No? I'll go ahead and talk about it. What the hell? I'll ask the question. Jeff, what the hell's a removable discontinuity? Oh, okay. I'll talk about that. All right. So here I might do this. Let me see if you guys can handle this. I'm going to erase this. I've captured it up here, what we did. So I'm going to erase this part. Let me show you something kind of nifty. This method, I did not name this method. Everybody has a method to do this. Hopefully something more than just plug it into an app and see what it says. Hopefully you have a way you can do it. Let me show you a different way. I'm going to take 3. I'm going to actually move it over there. Which means at the end, what am I going to have to do? I'm going to have to move a factor of 3 back to the front. Right? So this is not, so I've kind of entered the realm of not really the problem anymore. But this is much easier. Well, how do I factor this?
Plus 12.
Yeah, plus 12. Minus
4.
Okay. Now watch. This would make negative 4x here, right? And this would make 12x. So let me take a factor. Remember I took a factor of 3 and I took it from the front to the end? Let me take a factor of 3 and take it from that and put it back in front again. You see how I get negative 16 now? So now I'm back to the normal problem. So this was all like intermediate stuff. This isn't, there's nothing I could do to go here to here algebraically, legally. But this is a method. This is actually called the Texas slide. I have no idea why, but it's just the name, right? How do you get the 1? What do you mean the 1? Which one? Do you mean which one? There? This one? Is that the question? Oh, so I have equal degrees, right? So you have to know the 3 situations. If the bottom degree is higher, what's the horizontal asymptote? If the degree on the bottom was higher than the top, what would be the horizontal asymptote? 0. Because the bottom dominates. It just kills the whole thing. Dividing bigger, 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 the whole thing can't take it. It goes to 0. If they're equal degrees, then it's lockstep with each other. When x gets big, these don't mean shit, and that would be just 1. That's where 1 comes from, right? If this was 6 and this was 3, that would have been 2. So if the degrees are the same on the top and the bottom, the shortcut for the horizontal asymptote is y equals the ratio of the coefficients. We've talked about that before. I explained why that's true. All right. And the final one, of course, where does slant asymptotes come from when which degree is higher? Yeah, when the top degree is higher, it goes to infinity. A slant asymptote is the method by which it goes to infinity. So those are the 3 things that could happen for horizontal asymptote. You like it? So finishing this up, I get x equals negative 4, x equals 4/3. And these are my whats again? What are these?
Vertical asymptotes.
Vertical asymptotes. I like it. So let me put it over here. Horizontal asymptote, y equals 1. Vertical asymptote, x equals negative 4, x equals 4/3. Become a 3. All right, cool. I like it. Did I leave anything out? I don't think so. That's pretty much all we need. And then I can maybe pick a couple of points as anchor points to help me out. Okay, let's try this. I'm going to erase all this. So I'm going to ask you, part A, find all the intercepts. Part B, find the asymptotes, right? And then I'm going to ask you to graph the bad boy.
I have a question.
Yes.
How did you get a -4?
Oh, all right, shit. So
Sorry.
that's all right. That's all right. Were you okay with how we factored this eventually?
Yeah, I got the same thing, but I got +4, 4/3.
You got both of them positive? Is that what you said?
Yes.
But it can't both be positive since that's negative. They have to be different signs. Do you see that?
Yes.
So they can't both be negative. They have to be, one is positive and one is negative. So then you get -4 and positive 4/3. Is that okay?
Yes.
Okay, cool. I like it. And again, you don't have to do the slide method if you don't want to, right? Real quick, just to show you, if I were to do it the other way, 3 times -16, 12 and 4, make the 12 positive, the 4 negative, split these up. All right. And then group. And then you get x plus 4 and 3x minus 4 equal blah, blah, blah. Okay. So that's kind of like your traditional way to do it. The Texas slide is just a little quicker. And if you feel comfortable with the numbers, then you should be able to do the quicker method. All right. So let's see what we got. We got x-intercepts here. It's going to be a little bit longer in the positive direction. Going to figure out what our scale here is going to be. So let's see, -1/3, 0, 5, 0. And then I don't know yet what the scale is going to be. I got an asymptote at 1. I still don't know what that's going to be. Vertical asymptote at -4. My scale sucks. Oh, well, what else is new? Right, vertical asymptote at -4. Vertical asymptote at 4/3. So can somebody tell me a point that would, I really just need 1 point, to be honest, but I'm going to allow you to get up to 3 points to help you. Kurt, I think you mean a slant one, right? We're gonna look at a slant one in a minute. Which region do I not know anything about? Can you guys see how many regions have I broken this up into? 3. 1, 2, 3, right? And the function must exist in each of those somewhere. What's the only region I currently have no information for?
The far negative side?
Yes. So let me go ahead and throw that bad boy in. That's -5. So let's see, what is f of -5? I like it when it's, screw it, it's okay, Jeff. I like the factored form, but we can do this. Oh God, what's it, 75 minus 70. Wait. Oh, wait, -5. 75 plus 70, holy shit, okay. 75 plus 70 minus 5, so 140. Neat. So that is at 140. So let me tell you this. Let me show you a trick. Let me go to -6. Let me really, I want you guys to really understand. Did I really need to use -5? No. Do you see how the output was 140? Do you want to make a scale that goes up to 140? Not really. It would smush everything else. So let me go to -6. Somebody help me out. What do you get when you put a, oh, holy shit, Jeff. You didn't do the bottom at all. All right. Sorry, guys. I just did the top. Why did I do that? So this will be 140 divided by, Jeff. There you go. What am I going to divide by? 75 minus 40, 35, minus 16 is 19. And what is that? You guys can double check me. Make sure that comes out. Does that look right? And that's roughly 7. 7 point something or other. Everybody with me? That's about 7. That's good. Okay. So it seems like we could probably deal with that. Okay. So this, how does it have to look over here? Now that I've picked my scale is going to go by ones. I can handle going up to 7 there. This is already by ones. So how's it got to look over here? Let me go ahead and put my horizontal asymptote in. Yeah, I can kind of tell it's got to live here, right? It's got to live here. So it can look something like that. It's got to go slam up against that, and it's got to slam up against that one. So everybody with me so far? Now here, what do you know about this x-intercept? Each of the x-intercepts had a multiplicity of what? 1. Remember that? It was a 2. I had 2 x-intercepts. They have a multiplicity of 1. Where's my y-intercept? 5/16, which is about right there, right? So can you guys see what this, it's got to go through this, correct? So is it going to start here? Obviously not. If it went through, how the hell would it ever get back to this guy? So I know it's got to look something like this. And how do I know it looks like a cubish? Because it's got to go through those points. It's got to slam up against that wall, and it's got to slam up against that wall. It's almost the only shape it could take. Through, slam, slam. All right. But if you wanted to, let's try to figure out like f of -2, just to kind of double check where we are. You got to let me know the minute you have a question, right? If I don't hear anything, I'm just going to keep going. Okay, so somebody help me out. F of -2. Let's see, Jeff. Maybe we should write this down. No, screw it. 12, 40. Is that 35? Did I do that right? Maybe. You never know, Jeff. 12 minus 32 is -20. That's neat. I think that's what that is. I don't know. Does that sound? Why did the graph go through the why did the graph go through the horizontal asymptote? When does the horizontal asymptote actually exist? I know I draw it all the way across, but when does it come into effect? Does anyone remember? Where does a horizontal asymptote come from? Letting x get really, no, backwards. Letting x get really big. Horizontal asymptote is equivalent to end behavior. End behavior is what happens when x gets really big in both directions, right? So in the middle, it could go across the horizontal asymptote as much as it wants to. And to be very honest with you guys, it could go across the horizontal asymptote an infinite number of times. I think I've drawn this for you once before. But do you see how it keeps getting closer and closer and closer? That's what it's got to do. It doesn't say anything about not crossing. What's the whole idea of a horizontal asymptote? It must get closer to it. It says nothing about not crossing it. A vertical asymptote, why can I not cross a vertical asymptote? Because that is something that's not in the domain. That is a major problem, right?
I have a question
Yes.
about the same thing. Like, so when you cross it, there should be like a x value equal to 1. You know what I mean?
Oh, sure. All right. So when you cross this, there must be a place where the output of this is 1. That's
Yeah.
what you're saying. Yes.
Yeah. Yes.
Yes. Yes.
Oh. Okay.
So there must be somewhere. So I mean, real quick, this is an excellent question. And this is actually the way you determine if any graph is going to go across the horizontal asymptote. If there is somewhere, in this case, so if there is somewhere where this is equal to some multiple of this, I don't know if you guys are with me at all. If this is ever equal to some multiple of this, that means it's going to cross. So watch this. This is kind of neat. Is this ever equal to this? How do I solve this? This is all a side note, by the way. This is all a side note. This is neat. This must equal this at that point because the output is 1. Does everybody kind of get that? The output would be 1 there, which means this equals this. Well, how do I start to solve this? Well, these cancel each other, right? Then I can add 14x and add 16. You could do it, Jeff. What is that, 22x? So x equals 1/2. So and that's roughly where it is. Look at that. Jeff's graph is good. I'm surprised at myself. So at 1, this is a really good question, Rio Scott. It gets a little bit technical, but there is a place where the top equals the bottom and it's at x equal 1/2. Isn't that about where I crossed the horizontal asymptote at 1/2? Okay, that's kind of why. That was extra stuff. That's extra. But that's an awesome question. I like it. Okay. Oh, let's see. So yeah, this goes up forever. And then what's got to be true here? I mean, can I start up here?
No.
Not in this case, because it's got to go through this, right? Now, to be honest, there could be a function that would start up here. It would touch here, and then it could approach, but I don't touch this. I have to go through it because the multiplicity was 1. So just do this thing. So very often, the outer regions are simple. They're going to be contained within the walls. The inner one is the one that could do some freaky stuff. All right. Is this graph perfect? No. Is that bad? No, that's awesome. That's good. I like graphs that are not perfect because they should be made by humans, which means they are not perfect. Okay. Maybe. All right, what was it? I promised to do 2 things. Slant asymptote, and there was something else. Oh, I almost had it. Shit. Damn it. Any questions on this guy here? Okay, I'm going to erase this guy. You guys ready? All right.
Yep.
Oh, yeah, okay. There was a class I had, this one girl would always wait till about right now. She'd go, wait, just joking. Oh, shut up. Get out of here. All right, let's talk about slant, and then maybe somebody can help me remember what the other thing was. I got it. Wait. It's removable discontinuity. Let me write that down first. Removable. All right, this is written in this language of Jeff. All right, slant. That's just for me. That's why you can't read it. Now, of course, slant asymptotes happen when the top degree is higher than the bottom. So something like this here. Oh, that's neat. I like that. Okay. So you just have to remember how to do what? To find the slant asymptote. What do you have to be able to do?
Long division.
Long division. I love it. Remember, I showed you a situation where these were the same degree and that long division actually gets you the same answer that the shortcut does, but why would you do that? But still, it's good to know that the process doesn't care what the situation is. But this is where I have to use this to help me out. All right. And so you just got to remember how to do this. X squared times x is x cubed. X times 2 is 2x. Oh, Jeff, you got to get it over there. There you go, buddy. Line up your like terms, right? Minus, minus, negative 4x squared plus 3x minus 6. X squared times negative 4 is negative 4x squared. Negative 4x squared. Negative 8. Change the signs. 3x plus 2. How do I know I'm done?
Smaller than the divider.
Good. This degree is smaller than that degree. So it would make a true fraction, right? It's bottom heavy, not top heavy. And then when x gets really big, what's going to happen to this? It's going to go to 0 because exactly, it's always got to go to 0 because that's how I know I'm done, is when the top is a smaller degree than the bottom. So this is going to go to 0. That is the slant asymptote. So on your graph, you would have, you can graph this bad boy up, right? So up 1, over 1, up 1, over 1. Oh my God, my scale sucks like bad. Oh, well, didn't I? And so this would be one of your asymptotes. So if you had another asymptote here, then you got to figure out what it's doing on this side. It's either up here or down there. And what is it doing on this side? It's either in here or in there, right? So it's always the vertical ones that tell me how many regions I've got to figure out. Maybe. I know it can feel like there's a lot to remember. I like to look at it as there's a lot of things working with each other. Checks and balances with these things. All right. Ouch. Get out of my way. All right. Got too much crap here. All right. So is that okay for the slant asymptote idea? You guys all right with that? Let's talk about this, whatever that was. So here's the situation, and this is partially my fault. I should have talked about this earlier, but I kept thinking about it, and it never felt like quite the right time to put it in there yet, and then I just forgot about it. So if you look at this thing, let's look at this. What do you got, Jeff? I don't know. Let's do, sure. We'll make it easy. All right. So this is a reason why I don't know why I'm not doing this, but what I always do myself, if I'm going to do this problem, I factor everything first. And one of the reasons you do that is to look for this situation. So how do I factor the top?
X plus 2 minus 2.
And then how I factor the bottom?
X minus 4 plus 2.
Yes. So do you see how something happens, right? Does anyone notice something? Yeah, these cancel. So if this wasn't here, I really, now watch, stay with me. If this wasn't here and I got really close to -2, stay with me. Like negative 1.99999999999999999. That would be 0.00001. And then when you divide it, wouldn't that be huge? That's why it goes to infinity. But when I put that there, that is just the same as that. It would cancel. It doesn't let it get huge. So that's why something different happens for this. Is that actually a vertical asymptote at -2? No. But -2, is it in the domain? No. So what the hell happens there? Open circle. What do you do at a point that's not in the domain? You put an open circle there normally, unless it goes to infinity, and now you don't need an open circle there. Can't get there. So what would this thing look like if you cancel these out? right? Then you work with this, but you remind yourself that there's going to be an open circle. You can do it. Here you go. At -2, comma, what do you get when you put a -2 into this? I get -4 divided by -6, so I get 2/3. So there will be an open circle at -2, 2/3. That's some freaky shit. Where will there be a vertical asymptote? I think you said 4, x equals 4. And where is there an x-intercept?
2.
I like it. And the y-intercept would be 0, 1/2. Is that cool? Right? So these do go away. They cancel because the only place they would not cancel is at -2. If x was -2, because 0 divided by 0 is indeterminate. 0 divided by 0 is not 1. Now you'll learn if you take Calc 2, you'll learn that something that has this form could be 1, but it doesn't have to be 1. It could be anything. Anything from 0 to infinity or -infinity. It could be anything. Anyway, so that's a little too freaky for us right now, so let's not talk about it. All right. So when they say find the removable discontinuity, it's going to be at the point related to the part that cancels out. So in this case, the part that canceled out was -2, and then I can plug it in to see it's at 2/3. So let's do this. Last thing I'll do for this problem. Let's plot this in the calculator. Let's plot this in Desmos. I'm curious, to be honest. I really don't use Desmos too much. I'm curious what Desmos does with this thing. Holy shit, I've done something weird. All right, there we go. Everything just went crazy. Here we go. Here. Let me find Desmos. It's probably right there where it says Desmos. All right. What the hell was the function again? There we go. X squared minus 4. Let's see. I'm curious now. X squared minus 4 divided by, I guess I don't need parentheses, but too bad. What was it? X squared minus 2x minus 8? You could just look, Jeff. Yeah, it was. Okay. All right, now watch. Let's see what happens at 2. Let's see. Does it say anything to me? See, yeah, it doesn't have a way to. Oh, wait a minute. -2, -2. Ah, look at that. Do you guys see that? Do you see how it's got a little open circle there? Not in general. I wish it would put an open circle there just in general, but I sort of have to get lucky and get right on it. Let's see if I can do it again. I didn't realize how lucky I was the first time I did this. Ah, there we go. Okay. Oh, and it's an open circle there. Oh my God. Okay. So that's kind of cool. That's showing you that that's what's happening. Now watch. What would happen if I change this 4 to a 9? Can somebody tell me the main thing that would happen to this graph? What would be the biggest change if I change that 4 to a 9? Think about it. Say again.
Article.
Yes, there would be 2 vertical asymptotes because the x plus 2 one wouldn't cancel out now, right? So there should be another vertical asymptote at -2. So if I make this 9, there we go. Vertical asymptote at -2, vertical asymptote at 4. Because now there's nothing on top to cancel that other vertical asymptote out. Sweet. Yes, maybe? No? Too much? All right, thank you guys. Okay. Anything left over? Anything that we didn't talk about that still is troubling? Do you remember how to do Descartes, everybody? Okay. And you remember how to identify upper and lower bound? You think so? Okay. Can you do some from 5, 7? All right, let's take a look. What's 5, 7? Oh yeah, 5, 7. I think, didn't I tell you guys? Let me see real quick. I don't think I really put one on there from here. Let me double check. All right, there we go. I should just left this open. No. All right. Yeah, 5, 7 is kind of a silly thing. I know you guys have to do it for homework. Too damn bad. You should still do it for homework. But I really didn't put anything on there from, what was it, 5, 7. But if you have a specific question, we can look at it. Amanda, are you okay out there? I'm not up on the parlance. Okay, I don't know what that, I was like, what does that mean? Okay. All right. If there's no other questions, we're going to get back into where we left off. Do a little bit of new stuff, or maybe not new stuff really. Let's see. Yeah, so before we get into properties of logarithms, I want to focus on the graphs of logarithms for a little bit, because they're basically kind of new to us in this class. Some of you guys might have seen them before, but they're basically new. So let's look at some more about logarithmic graphs, and then we might tease a little bit about logarithmic properties. Okay. Go. All right. So let's do this. All right. If I ask you, give me a basic x cubed, right? If I just said, draw me no scale, just the shape, you're all able to do that, right? Yes. All right. Thank you, everybody. All right, good. So you got this guy. Wah! Okay, that's beautiful. That sucks for a problem. You have to graph a function, but that's beautiful for just tell me what this looks like. And then of course we got square root of x. We all know the shape of this, right? Looks like a parabola that fell over and lost its bottom half, right? And now we got, well, let's not do that. We got to talk about that yet. 2 to the x. What does that look like? This is semi-new. Yeah, there you go. It's got an asymptote there, and then it goes crazy. I like it. I like it. So as it goes backwards, it cuts in half, cuts in half, cuts in half, cuts in half. And that's why it never gets to 0. And as it goes forwards, it doubles and doubles and doubles and doubles. And that's why it kind of grows uncontrollably there. Yeah, I like it. So we have to know, the more you know the shapes of these things, the less points you have to graph for a problem like we did before. Like if I said graph this, right? You could identify the shifts. What would the shifts be?
Right 2.
Right 2?
Yeah, up 3.
Up 3. So then you would do the basic graph. You got 0, 0, you got 1, 1, and you got 4, 2. There's your anchor points. And you got the shape of it. And then each point you take right 2. Why did it do that? Gummit. Right 2. And then up 3. That's an excellent choice, Jeff. Right 2, up 3. And then you take this point. What did I do? Yeah. Right 2, up. That's not too bad, I guess. Right 2, up 3. I think I got those 2 points, and that's enough. And then you got the shape. Yeah. You should take that point, but oh. Right? Nothing major. We've done this quite a bit. And it does not care what the function it is, it lives inside. Right? So how would I do if I could just use the space on this whiteboard better? It would be so awesome. All right, so just keep that in mind. right? So let me write the next function we're going to work with, and then I'll erase this. What about this function if I have this function? 3 to the x minus 2 plus 3. What would the shifts be there? What shifts would happen in that one?
Same.
Same. All right, I like it. This one, try not to erase it. Doesn't care what function that lives inside. There's a minus 2 next to the x. Okay, that's right 2. And there's a plus 3 outside. Okay, that's up 3. It doesn't matter what the freaking function is. The shifts do the same thing, no matter what. So I'd start with my 3 anchor points. -1, 1 over the base. 0, 1, 1, the base. And then I would shift each point right 2, up 3. So this is actually going to be like right there. Oh, well, that's too bad. I could do it in a different color. That would be so smart, Jeff, considering you actually have different colors down there, buddy. There you go. Right 2, up 3, 1, 2, 3. And of course, right 2, up 3 would be up here. Ooh, where's my asymptote go? Does it care about right 2, the asymptote?
3.
Yeah, it has to go up 3. So it'd be right here, which kind of makes sense. It goes along with this. Yeah. All right, so you got your base points. You draw a little dotted line. That's your base function. And then you apply the shifts to each of the points. So it's knowing the shape, knowing some base points, and then shifting them. Bam. I don't want to see any more XY tables. You plug in shit into this. That's not the point, right? We're better than that. We don't need to make XY tables. Okay. All right, maybe. Okay, so just to change things up a little bit. Let's look at my next function here. Actually, we got to first do this one. Let's all remember how the hell this works. How would I graph that thing? So I gotta kind of develop my anchor points. I know the shape of this, right? What's the shape of a logarithm? Do you guys remember? Yeah, just remember it's like an exponential just this way. So the shape of a logarithm is this. That's a logarithm for the next of the asymptote there. All right, let me stop. So now I just got to figure out what are my anchor points? And then I could do the same thing we did before if they give me something that's shifted, right? So my anchor points, I could use. So what I like to do is, well, all right, let's start with 3. That makes sense. Why does 3 make sense to throw in here? Because what's log base 3 of 3?
1.
1,
Yeah.
yeah.
1. I like it. So what's another smart thing to plug in there? Let's see if you guys can get this. What about 1? What's log base 3 of 1? What do I raise 3 to make it 1? Yes. 0. All right. And you can kind of think about these backwards. When would the answer be -1? So that would be 3 to the -1. So what must have been inside?
1/3.
1/3, yeah. So these are my anchor points. If you'll notice, they're the same anchor points as the ones I used for 3 to the x, just reversed, of course, because log base 3 of x is the inverse of 3 to the x. So they're the same 3 anchor points, just reversed. So let me graph these. So 1, 0, 3, 1, and 1/3 -1. So here's my asymptote. Crappity doodah. Well, it's not horrible. should be going up forever, but all right. So now if I ask you to graph this graph, how would I shift these? What would the shifts be?
Left to 1,
Yeah, so it'd be left 1,
up 2.
up 2. Where does the asymptote go? Does it care about up 2? No.
1.
Yeah, so it's gonna be a -1. Right? The asymptote, if I move it up 2, okay, it doesn't care. It just cares about the left 1. Okay. So now I take every point. So I'm gonna go left 1, up 2. Right, where am I? I think I'm in the right place. And then I'm gonna go, yeah, left 1, up 2, left 1, up 2. And then here's my graph. Wow. I don't know why I'm sucking so bad tonight. Oh, it's not too bad. So you can see it's the same graph, it's just been chip, chip. So it's really good to draw the asymptote first, because it is kind of like a guide for the rest of your graph. Okay. Is that okay? I mean, it's nothing new. It's not new. We learn a new function and then we shift it, and that's old shit, right? So when we learn trig functions, guess what we're gonna do to them? We're gonna shift them, all right? We're gonna reflect them. We're gonna do all kinds of weird shit to them. They'll have different names, but they'll be the same stuff, right? So we call it, if we stretch one of those, we call it changing the amplitude, but that we'll wait for that. They have little different names. Sort of like the perimeter of a circle is the circumference, right? Same kind of idea, different name, same thing. Okay, maybe. So here's the only real new idea for tonight. And I want you to understand the idea behind this. How do you write a cube root? How do you write a cube root? It would be cube root of x, right? Whoa. So how about a fifth root? Well, you put a little 5 with the x. How about a square root? How do you write a square root? You just put a thing. Why don't we put a 2 there? Shouldn't there be a 2 there? There is a 2 there. There is. It's just understood to be there. I really want you. It can't be the first root. The first root wouldn't make any sense. The first root would be like, what's it take 1 up to make 7? 7. So what the hell do we need a first root for? It's crazy. So we don't put the 2 here. Why do you think we don't put the 2 there? Why didn't we pick 4 to be the one we don't put the 4 there or something? What do you think?
It's the first one. That makes
Okay,
sense.
I like that. It's the first one. But that's not quite, I understand that. And that makes sense. But more importantly, the most commonly used root is the square root. So that's why we decided the only one that doesn't have a number is the one that we're going to use the most, because we're math people and we're lazy. If we don't have to write something like, sounds good to me, I don't have to write that 2 every time. Yes. So now watch this. Which base for the log? This is going to be a little weird. How else can I say this? All right. What's our number system based on? What number is our whole system of numerals based on? Don't say 1. Like this, watch. What does this number mean? What's that number mean? 4. Oh, you're all like, we've gone to math 0. Okay, Jeff. That's 400, right? And 30, 3 tens. So our number system is based on
Tens.
tens. I like it. Quick side note, the Babylonian numeral system was based on 60s, which is where we actually got our idea for how we keep time. and how we do longitude, latitude in minutes and seconds. 60, 60, interesting, neat. Why did they do that? Because 60 times 60 is close to the full year, and for ancient civilizations, harvest time would be very important, so they put everything around the length of the year. Isn't that neat shit? All right, that's enough, sorry. All right. So different civilizations had different bases for their number system possibly, but the most commonly used one was 10 because we have 10 fingers. If we had 8 fingers, we would have used a base of 8. Okay. So when I'm never going to write this again. This is weird to me. This feels weird. It's sort of like, isn't this look weird? Doesn't that look weird to you guys? No? Nobody else? That looks weird to me. This looks equally weird to me because that's the one that we chose to not show up. Just like we chose the 2 to not show up. For the same reason. It's the most commonly used logarithm. That's why the name of this, base 10, is called a common logarithm. So when you see in the book, they talk about the common log. That just means log base 10. So what is log of 100? What is that? Yes, 2. What are you thinking to yourself? What does 10 need on it as a power to make 100? 2. I like it. Now, oh yeah, all right. I'm just remembering something I promised to show you from last time. The other base that's weird for logarithms is related to E. And I promised you last time I would show you something kind of nifty. If I graph y equals 1 over x for x greater than 0, stay with me. I'm going to graph y equals 1 over x for x greater than 0. It would look like, let's graph a few points just to, so 1, 1, 2 would be a half, and 1/2 would be 2. You with me? If I plug 2 in there, it's a half. If I plug a half, all right, you guys get the idea. So there it is. If I do, let me see how I can say this. I want to figure out the area. So this is so cool. Do you guys see how there's an area here underneath that function? This is an area. So I'm like, how far would I have to go up until the area becomes 1? That's a weird question, isn't it? I know, it's a very strange question. But here's the cool thing. The answer to that question is you would go up to E. If you stop at E, the area here is exactly 1. That's some shit. That's some cool shit, right? And that kind of freaks people out. All right. So when you get to calculus, whoever your teacher is, ask them about this the minute you learn something called integration, right? So if you take calculus, you get to this point, go, what was that weird shit that other guy was talking about? Oh yeah, E in this thing. Okay. Now, look at this for a second. Here's what the book was talking about, but this is kind of a neater way to look at it. Think about what happens to this when n gets really big. What is the inside? So watch this. Let me introduce some kind of nifty notation. The limit as n goes to infinity. So remember I said this earlier to some of you guys, limits are going to be in calculus. But this just means let n go to infinity. What happens to the inside? If I let n get really, really, really big, what happens to 1 plus 1 over n? What happens to 1 over n if n gets really big?
Small.
Good. So what happens to 1 plus 1 over n? It's going to go to what?
Big.
It's going to go to
Big.
This goes to 0. So this goes to 1. Does it ever get to 1? Beautiful. It will never get to 1 because this is never equal to 0. It just goes towards 0 forever. I don't know how well. So again, this is just the idea of an asymptote, right? We've talked about this idea before. I just haven't used this symbol, and this is the kind of symbol I could use for asymptotes. But what's this doing? That's just straight up getting freaking huge, right? So if the inside did get to 1, what is 1 to any power? It's 1. But the inside never gets to 1. It's always something a little more than 1. So do you understand there's like competing things happening here? If this got to 1, the answer would be 1. This is getting crazy big. This never quite gets to 1. This wants to make it stupid big. This wants to make it 1. They're kind of competing. And the really neat thing is, here, let's do this. Somebody give me a big ass number.
1,000.
1,000.
20.
I'm always waiting for that answer. All right, let's stick with 1,000. Can you guys do this in your calculator real quick? What's 1 plus 1 over 1,000 to the 1,000? What's your calculator say that is? Here, let me do it with you. What do you guys get? Anybody? Anybody? Yeah, so I get
I'm sorry, what's the question?
1 plus 1 over 1,000 to the 1,000 power. So that's what I get right there. 2.717 basically. All right. Oh my God. Help me. Oh, there you go. Okay. So I get 2.717 roughly. So let's do 1 plus 1 over, let's do this. Well, screw it. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Let's see, that's 1 followed by 9 zeros. So 1 followed by 9 zeros. Let's see what that is. Oh, let's see if the calculator likes this. All right. Who else out there is having fun? Probably just me, I understand. A very strange person. Let's see. 1, 2, 3, 1, 2, 3. Yes, baby. What do you get?
Seven, 1, 8.
Yeah, 718, 28, blah, 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 blah. I like it. That is basically what E is. E is defined to be the limit as n goes to infinity of 1 plus 1 over n to the nth. It is also the area. It's also the place you're going to stop so that the area is 1. It's really interesting that it comes from such different places, right? You might notice that this function is actually a part of this expression, so there is a connection. Okay, I like it, maybe. So it comes from a very different place than pi did. Pi just comes from taking any circle and dividing its circumference by the diameter. You always got the same number. Civilizations went crazy, and they're like, oh my God, it's amazing. This comes from a very different place, but since it is an irrational number, we gave it a letter just to make it really easy to identify. I like it. Cool. So let me see if you guys can do this for me. What is the inverse function? Can you please find the inverse function for this? What's the inverse function for that? It's not a big question. This is a very easy question. No work to do. We know what this is. What kind of function is the inverse of an exponential? Holy shit. Are you guys there? That everybody could see should just freeze and maybe he'll think we're frozen. No,
Oh, they're typing in chat.
It's an interesting thing, but there is no such thing really as an xth root.
Isn't it refracted?
I love you guys so much. So remember, we started with an exponential and we graphed the inverse. And I said we have the graph before we know the function, and then we developed the symbol, and the symbol was log. It's log. It's log. Everyone, log. No, nobody gets that reference. Okay. So this will be log base 4 of x. What is the inverse function for 10 to the x? See if you guys can do this without driving me crazy.
Log X.
I love it. Perfect. Good. We don't write that freaking 10, just like we don't write the 2 on the square root. Now, what is the inverse? Get out of my way. Get out of here. What is the inverse of e to the x? All right, you guys don't know yet. What would you say? Some of you guys might know. But you would start by saying what? Log base
E.
E. All right, now that is the absolute last time I'm ever going to write that. That is an abomination. So what do we use instead of this? We actually use natural log. ln. ln is the only symbol that doesn't say log, and it's only used for base E. And yes, there's a whole history about why we call it natural logarithm, because E is the most useful base for population growth. So throw some rabbits in a room, give them some food, let nature take its course. They're going to follow an exponential explosion of rabbit population. Don't think too much about what that means. All right. Little rabbits, who cares? Little rabbit monarchy, right? They have a little rabbit king and all that kind of stuff. You got to keep the blood pure. All right. So natural log of x is the newest symbol. It's just for base E. All right. Oh, that's pretty good. All right. Yeah, I managed to get everything out there that I wanted to. So that's it. We're done. Let me know if you need to hang out. Otherwise, you are free to go to wherever you're legally allowed to go.
Thanks, Prof.
You're welcome, Stude. Don't
Thank you,
forget
Professor.
the quiz should be open now. So if you want to start the quiz, you can start it now if you want to. You have until tomorrow at 7. Everybody good? All right, I'm going to head out. I'll see you guys